Good morning and welcome to this the lecture number 23 of the course Water Resource Systems, Modeling Techniques and Analysis. In the last few lectures we have been talking about reservoir systems. So, initially we started with capacity determination, that is the minimum capacity required for meeting a certain demand patterns for a given sequence of flows. And then we went on to discuss the storage yield functions, where we are looking at the yield in terms of the maximum constant release that can be maintained from a reservoir for a given sequence of inflows. And then we looked at the optimization problem, by which we can still achieve the storage yield function by maximizing R. So, essentially in the last lecture what we did is that we solved an example for storage yield function with respect to the storage, that is the capacity, storage capacity of the reservoir. What is the yield that we get for a given storage capacity is what we did, and through this example we showed that in general it keeps on increasing, the yield keeps on increasing as you increase the storage capacity, but after a time it remains constant. So, indicating that no matter how high the storage you provide beyond this particular point, the yield will still remain the same, and as I mentioned in the last class, this is because of the inflow limitation. And then we went on to solve the same example using a mixed integer LP formulation. This is where we stopped last time. So, let me just go through it. So, what we are looking for is the constant release, which is the maximum constant release is what we are looking for. So, maximize R and then we put this R here. Remember, it is not RT, but R, which means it is a constant across time. And then we included explicitly the spill term here to make sure that the spill as you obtain from the solution is non-zero only when the storage reaches the capacity. We include, to ensure that condition, we include the integer variable. So, beta t here is integer variable and typically it is a binary variable, which means it can take on either 0 or 1. Just look at this formulation. I explained this in the last class, but for completeness sake let me repeat it. What we are saying is that beta t is an integer which is less than or equal to 1, which means that beta t can take on a value either of 0 or 1, because being integer less than or equal to 1, it can only assume either 0 or 1. And look at this condition, St plus 1 divided by k, and St plus 1 is the storage at the end of the time period or at the time period t, or storage at the beginning of the time period t plus 1. So, if that is greater than k, what happens? This will be more than 1, and because of this condition beta t will take a value of 1. So, whenever the storage exceeds the capacity, beta t takes a value of 1. If this is less than k, then this ratio will be less than 1, and therefore, beta t has to take a value of 0. Now, when beta t is 0, which means that the storage is less than the capacity, you do not want any spill there. Beta t is 0, you put by virtue of this condition, spill t is less than or equal to beta t into m. When beta t is 0, spill t has to be equal to 0, and beta t is 0 only when storage is less than the capacity, and therefore, you will make sure that spill is 0. When beta t is m, you want a non-zero value for spill, which will satisfy this, and to make sure that you get a non-zero value of spill, you multiply beta t by some large number m, so that you have the flexibility to choose spill t to make sure that this is satisfied correctly. So, beta t into m, where m is a large number, in fact, spill max or some the maximum value of spill that is possible at a reservoir, etc., you can use. So, this will be spill t is less than or equal to some maximum value, that is the idea there. So that you will get at beta t is equal to 1, which happens only when S t plus 1 is greater than or equal to k, as determined from this, you will get a non-zero value of spill. So, this is how we include, and all other conditions we have explained earlier. We know these are same conditions that we use everywhere, S t is less than or equal to k and so on. Then towards the end, I just introduced the problem of reservoir operation. Recall that the reservoir operation, which is the single most important problem in water resource systems, is the one dealing with deciding on the release sequences across time periods. Remember, you are talking about large volumes of water here, and therefore, how we operate the reservoir is an extremely important problem on the field. And therefore, at the planning level, that is, you plan the reservoir operation in a certain manner, keeping in mind or keeping in view the likely inflow sequences that are coming in the year. So, typically we use the historical data and then derive the reservoir operating policies. By reservoir operating policy, we mean sequences of reservoir releases across time periods as a function of the state of the system. Now, the state of the system can be storage alone, or storage and inflow together, or storage, inflow and rainfall in the command area, storage, inflow, rainfall and soil moisture in the command area, etc. So, as much sophistication as desired can be put into these models. So, that is what we defined as reservoir operating policy. And the simplest of such reservoir operating policies, which commonly is adopted intuitively in most of the reservoirs, especially in India, is the so called standard operating policy. The standard operating policy is simply to meet the demand in a particular period to the best extent possible, without looking at other periods. So, simply look at the water available in this time period, at the beginning of this time period, which is typically S t plus q t, that is the storage and the inflow. Of course, the inflow will occur during the time period, but while deriving the operating policy, you will say S t plus q t is known. That means, the storage at the beginning of the time period plus inflow during the time period. Look at the total water available and then compare it with the demand. If the total water available is more than the demand, simply meet the complete demand. If the total water available is less than the demand, you empty the reservoir, put all the water to meet the demand. So, which means meet the demand to the best extent possible from the available water is the standard operating policy, and whenever the water is in excess, you store the water. So, the level in the reservoir keeps on increasing until it hits the capacity. We are still talking only about the live storage. Remember, always whatever terms that I am using here, S t, K, etc., they all refer to the live storage. Once the reservoir level hits the capacity, anything beyond that after meeting the demand will go as spill. So, there is a filling phase and there is a spill phase, and there is a period in which not period really, there is a phase where S plus Q is less than the demand, that is the total amount of water available is less than the demand, that is the point where the reservoir will be always empty. So, this is how the standard operating policy is derived. Let us go through the standard operating policy, understand correctly what it means in terms of the actual operation. And standard operating policy, as we will presently see, is not an optimal operating policy. It is just as a rule, as an operating rule. For example, look at the storage, look at the inflow that is likely to come, and then make the release compared with the demands. That is all. There is no optimization involved here. So, let us start with the standard operating policy. Typically, it is shown as a graph like this. On the x axis, you see S plus Q. This is the storage plus the inflow. This is the total water available. Neglecting losses, that is. Now, this is for any period, for all periods in the year. Now, S plus Q and D is the demand. Let us say you are looking at some irrigation water allocation from the reservoir or municipal and industrial water allocation and so on. So, the demands are known. So, as long as you are in this region, that means your total water available is less than the demand, you make the complete release, which means whatever is available you release, which means this is a 45-degree line. So, this will be equal to S plus Q itself. Whatever is available you make the demand. So, demand was here, you were here, which means demand is much higher than the water that is available. So, you make the complete release, and therefore, after making the release here, this phase in OA reservoir will be empty. There was the initial storage, you got some inflow and then you made a release of the amount equal to S plus Q, whatever was in the storage plus whatever was the inflow, and therefore, the reservoir level will be at the bottom. Therefore, reservoir will be empty. So, reservoir will be empty after release in this region. Then once S plus Q is greater than or equal to D, what will happen? You will still make the release D only, just to meet the demand. But because S plus Q is higher than D, you are left with some water, and this water will start filling the reservoir. So, as you start going from the going to the right of D, there is a total water available to the right of D, the reservoir level starts filling. So, this is the filling phase. You keep on making the release D only equal to D. On the y axis is the release shown. So, this is release. So, we are saying that release will be equal to D whenever your total water available is greater than D. So, the reservoir starts filling up. Until what time it fills? Until your S plus Q, which is the total water available, after you meet the demand D, is greater than the storage itself, the storage capacity. So, until D plus K, which means this is the storage equal to K. So, you have filled the storage up to the capacity. Beyond the capacity, it will go as spill after meeting the demand. So, you meet the demand, but still there is an excess, and that excess goes as spill. So, this is the standard operating policy. Meet the demand to the best extent possible, fill the reservoir whenever there is excess water, and then spill over the reservoir whenever the reservoir is full, you have met the demand, and then still there is an excess water. That is all. You are not looking at what is likely to happen to the next time periods and so on. So, simply look at this present time period, look at the current state of the system in terms of the S plus Q, which is the storage plus the inflow, look at the demand and meet the demand to the best extent possible. So, as I said, along OA release is equal to water available, along AB release is equal to demand, and up to A reservoir is empty after release. At B and beyond, reservoir is full after release, and then there is a along BC there is a release is equal to demand plus excess water above capacity, that is a spill. So, this is the standard operating policy. Now, the same thing is explained here. I will not go through all these details, but it is available for going through. Exactly the same thing as I explained is written here. Now, in mathematical notations, we write it as follows. So, if ST plus QT minus CT, this is the evaporation, which was not included there in this term here. Here we neglected evaporation, but if you include the evaporation, you can write it like this. The storage at the beginning of the time period plus the inflow during the time period minus whatever is the losses. If it is greater than the demand, then you make RT is equal to DT. If this water available after taking out the evaporation is less than the demand, then the release is equal to water available itself, which is S T plus Q T minus E T. The overflow will be S T plus Q T minus E T, which was the water available, minus D T, which is the demand. When you meet the full demand from this, if this value is in excess of the capacity, this is the reservoir capacity. If this value is in excess of the capacity, then deduct the capacity and that will be the excess and that will be the overflow. So, what we are saying is simply that after the reservoir comes to the full level, after you meet the demand, whatever is excess, that goes as spill. So, that is the overflow, and then we obtain the storage. Then if this is negative, then obviously this will be 0. That means, there is no spill when the reservoir level is lower than the capacity level. Reservoir storage is lower than the reservoir capacity. Once we get OT, we get the storage at the end of the next time period. S T plus 1 is equal to whatever we started with storage is at the beginning of the time period, plus the inflow during the time period, minus the evaporation that is going out of the reservoir, minus the release that you made, minus overflow. So, this is the algorithm which defines the standard operating policy. We should be able to simulate the operating policy, the operation of the reservoir using the standard operating policy. And of course, because of this condition now, what happens? S T plus 1 will be equal to K if whenever OT is greater than 0, because of the way we calculate the OT. So, this is the algorithm by which we simulate the standard operating policy. I have seen, of course, I have shown in one of the earlier lectures how we simulate using the standard operating policy when I introduced the concept of simulation. But again, for completeness sake, let us quickly go through another example, because we are now talking about reservoir operating policies. So, we will start with the standard operating policy and then move on to optimal operating policies. So, let us take this example where we have the monthly flows Q T and you have the demands given here, and then the evaporation, average evaporation rates are given here. Now, when we specify E T like this, for example, E T is also in volume, that is the evaporation losses are also in volume. In general, what we are doing is that an average evaporation from the reservoir is what we are giving. We are not specifying the evaporation as storage dependent losses, which can also be done as I have shown in the previous classes, in one of the previous classes. But when we take this E T in volume units for a particular month, let us say June month has a evaporation of 10 million cubic meters. It means that over a period of time, we have taken the average of evaporation from the reservoir over a long period of time, and then that is what we are putting here. All right. Now, with this now, we will simulate the reservoir operation with the standard operating policy. Now, for simulation of operating policies, typically we specify the storage at the beginning of the first time period. So, we will say we will start with S 1 is equal to 200 million cubic meters. The reservoir capacity is 350 million cubic meters. So, we are starting with 200 million cubic meters, and then the inflow will start, and then we will release according to the standard operating policy, and then see how the reservoir behaves. Look at this mismatch between the inflow and the demand. Here the flow is more compared to demand. Flow is more here, flow is more here, flow is more here. This is the monsoon period, June, July, August, September, October, etc. But the actual water required is in the other season when the flows are smaller. So, you have 45 million cubic meters in flow, but the requirement is 203. 19 here, requirement is 203. Like this. So, there will be a period typically in monsoon regions like ours. After the monsoon is over, your flows will start reducing. In fact, they approach 0 very fast in most of the rivers, but the demand will start increasing because that is the Rabi season where the irrigation demand will be higher. So, this is what is the typical picture where the flows are smaller, you have large demands, and this mismatch is actually managed by the reservoir. All right, we will do the standard operation now. This is data, QT is data, this is the flow, this is inflow, and this is the demand, and this is evaporation, and so on. And ST is the storage at the beginning of the time period T, which is given. So, at the first time period we start with a reservoir storage of 200 million cubic meters. On this we add QT 200 plus 70.61 and take out the evaporation 10 units, that comes to 260.61. Now, this is the water amount of water available in time period T after accounting for the evaporation losses. Then compare this with the demand 51.68, because this is more, you meet the demand to the full. So, RT will be equal to the demand 51.68, and 260.61 minus 51.68 is less than the capacity, which is 350. So, K here is 350, and therefore, the overflow will be 0, because your storage at the end of the time period, which will be 260.61 minus 51.68, which will be 208.93, which is less than the capacity 350. Therefore, the overflow will be 0. This is the overflow or the spill. Now, this storage at the end of the time period becomes the storage at the beginning of the next time period. Again, look at ST plus QT minus CT, that comes to 13.68. Then look at the demand 127.85, because you have enough water here, you make RT is equal to DT 127.85. Then 613 minus 127.85 is greater than 350, and therefore, overflows will occur. You compute the overflows, which will be 613.68 minus 127.85 minus the capacity 350, that will be 135.85, and therefore, you end up with a storage of 350. Whenever there is a overflow here, your storage at the end of the time period must be equal to the capacity 350. So, make sure that you will get a capacity of 350 whenever there is a overflow, and the overflow is computed from, this is the total water available after accounting for the evaporation minus the release that you have made, and whenever there is a the water available is more than the demand, you make release equal to the demand itself. After making the release, you look at the water available and compare it with the capacity 350. If the water available after making the release is more than the capacity, that excess you account for as overflow, so that the end of the period storage will be equal to the capacity itself. So, this is how you simulate from time period to time period, and the end of the time period storage becomes the beginning of the time period storage for the next time period, and again you carry out like this. So, 350 comes here and so on, and then suddenly you hit a low inflow period. You look at this point here, the inflows were decreasing, and then suddenly you hit a very low inflow period, but the demands are very large, and you simulate it and look at the demands. Let us say demand is 203, but you have only 199.07. So, you release 199.07. Now, you have only 9.27, whereas the demand was 179, you release only 9.27, and therefore, there is a huge mismatch here that occurs. In standard operating policy, there is no way you can project. For example, if you had stored some amount of water, you could have met more demand here in these periods. That means, what I mean is, by sacrificing on meeting demands at certain locations, certain time periods when you had huge amount of water, you would have stored more amount of water and increase the storage, so that that storage will be available for the next time periods. But in standard operating policy this cannot be done, and therefore, in the standard operating policy you simply keep looking only at that particular time period and then meet the demand to the best extent possible. And then you can do several analysis using the simulation that you did. I have shown it only for a few periods here. In fact, I have taken only 1 year period and shown the operation, but typically what we do this do in simulation of using standard operation is that you take last let us say 20 years 30 years data. Your demands may be constant for different time periods within an year. So, if you have 30 years of inflow data, the demands may be varying from D1 to D12 only. The same thing, same demands will keep on repeating from year to year, but the flows are different, and you apply the standard operation the way I have shown here, simulate the data, and then you will be able to look at how the system performs under standard operation. What do I mean by performance of the system? You may look at the release and look at how many times you were able to meet the demand fully. Let us say you were able to meet fully here, etc. Like this you keep on looking at this, and then once you come to this point the demands are not met fully. Like this you can evolve several performance measures. We will touch upon the performance measures subsequently in the course, but this is how you simulate the reservoir operation using standard operating policy. However, standard operating policy is not an optimal operating policy. So, typically you will be interested in an optimal operating policy, and therefore, you will look now at optimization of the operating policy, where you will have a purpose of operation, purpose for which you want to operate the reservoir. For example, you may have the release going only for irrigation with its returns associated with the releases for in terms of let us say crop yield, or in terms of the monetary benefit that you can account for, or in terms of the revenue that you get, or in terms of the intangible benefit of providing the water to the farmers and so on. So, you may have certain objective with which you are operating the reservoir. This objective you quantify and put it in the form of a optimization problem, objective function, as we have studied earlier. So, the problem now is, given a reservoir of known capacity K and the sequence of inflows. So, Qt is known, K is known, determine the sequence of releases RT that optimizes an objective function. Now, in general, when we are talking about reservoir operating policies, the objective function in a time period, what we are looking at is the optimization of the reservoir operation over a time horizon, and typically we begin with 1 year as the time horizon. The objective function which determines the value for the release as well as the value for the storage is in general a function of both the storage as well as the release. For example, you may make the release for irrigation, you get a return, but your storage level may be contributing to the head for the hydropower, and therefore, the storage also has certain value and so on. So, you may have in general the objective function as a function of both the release as well as the storage. Okay, we will look at one of the simplest optimization problems, where we are looking at deciding on the release policies. There is a certain demand pattern or demand sequence that is known. So, you have dt which is the demand, this is known, and the capacity is known, that is the reservoir capacity is known. We are looking at meeting the demands to the best extent possible, and therefore, I will look at maximization of RT, which means that if you have let us say 12 time periods, R1 plus R2 plus R3 etc., this is a function that I will look for, and we meet the storage continuity This is evaporation loss. This can also be made as storage dependent losses as I have discussed earlier, but for the time being we will not worry. We will take average evaporation losses during time periods. So, this is the storage continuity and these are the spills overflows. In the actual solution of the problem, you may want to put the integer variables as we discussed just in the last class, also at the beginning of today's class. For overflows, to meet this continuity equation as a equality constraint in the linear programming, there are several ways of handling as I have discussed in the previous classes. You can use either the integer variables and then use the overflows or the spills. Now, I put RT is less than or equal to dt. Some of the these constraints the students must be careful. Many times mechanically we write RT should be greater than or equal to dt, because demands are there and we would like to make releases more than the demands. But when we are looking at maximization of summation of RT, if you make RT greater than or equal to dt, most of the time what will happen is the reservoir will be empty, because you are saying RT should be greater than or equal to dt. So, because we are making maximization of RT will be increased to the best extent possible, but we put an upper cap of demand, which means that in no time period RT should be more than the demand. That is a cap that we put, so that we have water available for other time periods. And we meet the continuity equation, and all of these are standard conditions, and ST plus 1 will be equal to S1. That is, capital T is the last time period. We say that the last time period is storage at the end of the last time period must be equal to storage at the beginning of the first time period. These are the constraints. So, we will run this. When we run this, remember for S1 we did not put a starting value here. You can do solve this problem for various starting values of S1, or leave S1 free and then let the optimization problem decide what is the sequence of storages and the associated sequence of flows. Now, typically this is what is done in defining the reservoir operating policies. That means, you leave everything free and then let the optimization problem decide what should be the storage at the beginning of the time period 1, beginning of the time period 2, etc., and then the associated release sequence. That is what we define as optimal reservoir operating policy. Now, this is all of this I have told earlier already. So, typically we may start with a given storage at the beginning of the time period. That is, you specify, like we did in the standard operating policy, we can specify that the capacity is 350, but my initial storage is only 200 or my initial storage is only 100. Then you start building the operating policy. In which case, what do? We add an additional constraint here saying S1 is equal to 200 or some such thing. So, S1 is equal to some S naught known value or some such thing. We can put this condition. There are lots of variants possible on this. We will just understand the simplest form first and then see what else we can do over that. Now, what we will do is, we will take the same data as we did for the standard operating policy and solve the LP. So, the data that I have used for standard operation, the same data, this data we will use and solve LP without taking S1 as 200 as we did in the previous case. So, we are not putting that condition that the storage at the beginning of the time period is 200. We will just relax that and then solve this optimization problem. There are two things that you must note. That one is the evaporation is the average evaporation, we are not making it storage dependent losses, you can also make it. The overflows, we are just including it as a continuity equation. If for the specific problem, if you come across problems handling difficulties handling the overflows in the continuity equation, you can use the integer variables, which I am not doing for this simple problem. All right, then we get the solution. So, what we did is that we solved this problem sigma RT and then put the continuity equation and put RT is less than or equal to dt and all other conditions and solve this LP problem and t is equal to 1 to 12, there are 12 time periods. We use the Lingo software for this particular example and then solve this. We get the solution, this is all data, the solution will consist of ST, RT, OT and of course, ST plus 1. So, this part of the table shown here, this part is solution from the optimization problem. So, we come with a storage of 10.36 at the beginning of the time period. Remember, in our model, we left the storage is free. That means, let the optimization choose what are the optimal storages that need to be maintained and so on. So, we come with this storage 10.36 and release is 51.68 because your flow is more and so on. So, you can just check for each of the time periods, you can check the storage continuity whether it is maintained or not. That is 10.36 plus 70.61 minus 51.68 minus 0 must be equal to minus 10 of course, which is the evaporation loss must be equal to 19.2. So, these are the optimal storages that you get and these are the optimal releases that you get. Notice that this ST plus 1 will be equal to ST here, much the same way as we did for standard operation. Now, in this simple example, you may get a solution just similar to the SOP. For example, your storage, if you started with storage is equal to 200, perhaps you will get identical result as you obtained in SOP, because this is a very simple optimization problem, where we are simply looking at maximization of R. We are not saying that the deficit should be minimized or something, simply we are looking at maximization of R. Now, this will define the policy. How do we define, how do we communicate the policy to the operators is by saying that on an average in a year, you have this kind of inflow pattern. Now, these may be average inflows for the different time periods, June, July, etc. For these kind of average inflow pattern, you maintain this reservoir storages 10.36, 19.29, etc. and make these kind of releases as the flows come. So, the policy is indicated in general as the end of the period storage that needs to be maintained for each of the time periods, and you provide it in terms of a rule curve. That means, you maintain the rule curve shows that you maintain this kind of reservoir levels or reservoir storages at the end of given time periods. Now, that is what we do from this. Let us say that you start with time period t is equal to 1, desired reservoir release or storage volume at the end of the month. So, storage at the end of the month is what we are showing. So, at the end of the month you may have 19.29 and this is how you show the storage levels, and at the end of 12th time period you may get 10.36 and there may be certain periods in which you may have storage of 0. So, this shows the policy. Of course, remember that this is by far the simplest optimization problem that we solved, but in general this is the procedure that you adopt. You solve the optimization problem, obtain the storages and then specify the policy of maintaining the storages. Associated with these storages, remember there are also optimal releases that you are maintaining for meeting this kind of demand patterns. So, this is how you specify the operating policy. Now, in general, in realistic situations, you will not have such a simple demand patterns. You may also have flood season, you may also want to meet the demands in industrial demands during certain time periods, which may have higher weightages. You may want to meet municipal demands for drinking water purposes during certain periods, which may have much higher weightages and so on. So, you may have multiple objectives. Keeping all those things in mind, you can put the optimization problem, you can formulate the optimization problem and then arrive at the reservoir operating policy, but the general principle remains the same, that you formulate the I will repeat, you formulate the optimization problem with certain objective function that reflects the objectives of your operation, reservoir operation, solve the optimization problem, you will get the storages as well as the releases in general, and then formulate the policy of maintaining the reservoir storages at the end of the time period across different time periods within a year. So, in the end you must be able to specify what is the level, reservoir level that you need to maintain at the end of each of the months, let us say June month, July month and so on. So, this is what we call as optimal operating policy. As we progress, and perhaps in case studies that I discuss, I will indicate how complicated or how complex the problems can be, but the principle still remains the same. You formulate the optimization problem correctly and then solve it and provide the policy, reservoir operating policy, in terms of the storages as well as in terms of the releases. Okay. Now, so far we have been talking only about single reservoir systems. We discussed the problem of determining capacity for single reservoir. We also discussed at some length now the reservoir operating policies, both the standard operation as well as the multiple as well as the optimal operation. And in earlier one of the earlier classes where I introduced the multi objective optimization, I had talked about the single reservoir having different objectives, flood control, hydropower, irrigation, etc., which may be in general conflicting with each other. How to address multiple objectives which are typically conflicting with each other in an optimization problem, we know. But so far we have not discussed, except by way of mentioning in the simulation topic, we have not discussed specifically the multi reservoir operation problems or multi reservoir systems. Now, we will start looking at multi reservoir systems. Remember, we are still talking about deterministic problems, where there is no uncertainty associated with either the inflows or the storages and so on. Now, let us look at multi reservoir systems, and typically when we are talking about water resources development, water resources management and so on, our scales are spatial scales are large, and we are typically talking about several reservoirs, maybe 2 reservoirs, 4 reservoirs, 5 reservoirs, 14 reservoirs, 18 reservoirs and so on. If you look at cases like Narmada River or Tennessee Valley Authority, Damodar Valley Corporation or California Valley Corporation reservoirs, California Valley Authority reservoirs, I am sorry, it is TVA, that is Tennessee Valley Authority or California Valley Corporation reservoirs and so on. When you are looking at such systems, you typically have large number of reservoirs, and these reservoirs together have to be optimized as a single system. Some action that you take at one of the reservoirs is likely to affect some other reservoir. Some action that you take simultaneously at several 2 or 3 of different points may affect the reservoirs downstream of that adversely, and some action that you take during certain time period may have its effect in some other time period within the year. And therefore, the multi reservoir systems have to be looked at as an integrated single unit, where the flow, not necessarily the river flow, but the flow of actions, flow of different components are all integrated together. So, let us look at one simple example. We will start with a simple example just to understand what complications can arise in multi reservoir systems. So, we look at 3 reservoirs here. There is a main stream of the river on which there are 2 major reservoirs. We will call it as reservoir 1 here and reservoir 3 here, and on the tributary from the side there is another river that is joining, tributary is joining this main stream, and on that you have another reservoir here. So, this is reservoir 2. So, we will start with a simple reservoir system of 3 consisting of 3 reservoirs, 2 and 3. Now, we will just understand the continuity, very simple continuity. There is a inflow that is coming and adding to the storage at the reservoir 1. This inflow is because of the catchment of this reservoir. So, there is a catchment of this reservoir and that is what is contributing to this inflow. Similarly, there is a catchment here that is contributing to this inflow. When you come to reservoir 3, so what happens at reservoir 1 here is that the flow joins, this is the flow in time period t at reservoir 1. So, we are indicating Q1 t as the inflow in time period t at reservoir 1. Similarly, Q2 t is the inflow in time period t in reservoir 2. Then you also have because of the catchment here, there is also an intermediate catchment. All of this is an intermediate catchment for reservoir 3. So, the reservoir 3 receives water not only from the reservoir 2 and reservoir 1, but also from its own catchment. So, you may have Q3t here as the flow in time period t at reservoir 3 due to its own catchment in between. In addition, it also receives water from reservoir 1. Let us say you made a release of R1t from the reservoir 1, part of it may come and join this reservoir in general, because some of them it may have been utilized and only some part may come and actually join this reservoir. So, we will indicate it as alpha 1 R1t, where alpha 1 is the fraction of the release that joins the downstream reservoir. Similarly, from the release that you make from the reservoir 2, some fraction comes and joins this river and subsequently the reservoir 3. So, alpha 2 into R2t is the amount that is coming from reservoir 2 and joining this particular reservoir. Now, we look at this reservoir as this system as an integrated whole and formulate an objective function, formulate an optimization problem for this. So, we are looking at the simultaneous operation or the integrated operation of these 3 reservoirs. The reservoir 1 may have its own objectives, reservoir 2 has its own objectives, 3 has its own objectives, but because reservoir 1 and 3 I am sorry 1 and 2 here in this case are contributing to reservoir number 3, the objectives are all linked, because what you do at reservoir 1 will affect reservoir 3, what you do at reservoir 2 will affect reservoir 3, and therefore, you need to look at this operation as this system as an integrated unit. So, we will see here what we will do is, for the sake of formulation, we will say that this system serves a purpose of water supply, flood control and hydropower generation. That means, at each of the reservoirs you have water supply, let us say you have irrigation water supply, then you also have flood control, which means that during the flood season you may want to retain certain flood freeboard, so that you can absorb the flood waters, and you also have hydropower generation at each of the reservoirs, and therefore, the individual reservoirs have their own purposes to meet. In addition, they should meet the total system's objectives. Then release for water supply is passed through powerhouses. In general, it may happen that part of the release that you make for irrigation also goes through the powerhouse. Then we can neglect the losses in the powerhouse, although you can also account, it is not a great deal, you can just account for the losses as some percentage of the water that is released into the powerhouse and so on. for this simple problem, what we will do is benefits from powerhouse are expressed as a function of storage alone. In general, and in fact, this problem I will explain in perhaps in the next class. In general, for hydropower generation, what happens is the benefits in terms of the power that you can generate is a function of both the storage as well as the release through the penstocks, because you can recall gamma QH is the power that is generated, where Q is the discharge and H is the head and gamma is the unit weight of water, and therefore, power is proportional to power that is produced is proportional to both Q as well as H. Whereas, in this particular problem for demonstration, what we will say is that the benefits or the returns that you get from hydropower is simply related to the storage. We will not worry about the release as far as the reckoning of the benefits is concerned. Now, we will say B1T, B2T, B3T are the net benefits associated with unit release, unit available flood freeboard and unit storage for reservoir I. So, I will put a superscript I here to indicate that it is the reservoir and T is the time, and this 1, 2 and 3 are the reservoir. I am sorry, 1, 2 and 3 are associated with the purposes. For example, 1 is for the release and 2 is for the flood freeboard and 3 is for the storage. And as I just mentioned, the storage determines the benefits that you accrue out of the hydropower. Now, this is for unit volumes. For example, unit release, this is a benefit, and unit flood control storage or flood volume that you make available in the reservoir, this is a benefit, and so on. Now, a portion of release from reservoir 1 and reservoir 2 flows through to reservoir 3, as I explained, alpha 1 R1T and alpha 2 R2T, they come into reservoir 3. Further, we will say that there is a flood period. For example, in countries like ours, monsoon countries, you may say August, September, October and perhaps in some places November also, maybe flood periods, or maybe July, August, September and October, 4 months are flood periods. Now, during these 4 months, we may want to retain a certain minimum flood zone in the reservoir, flood absorption zone. So, we want to make sure that a minimum storage of F min I is the reservoir, at reservoir I, we want to maintain a minimum storage, buffer storage, which means that the storage level should not be more than a certain point, so that you have adequate buffer to absorb the flood waters, and that is what we are indicating here. At each of the reservoirs, we specify that during this flood season, which may be different for different reservoir systems, during flood season, we want to retain a certain flood freeboard. Further, the release that you make from a reservoir has an upper limit. A lower limit is of course 0, but it also will have an upper limit, because if you are making the release through a canal, then the canal capacity determines the upper release. So, each of these reservoirs has a maximum limit on the release. So, R I max is the maximum release that is possible from reservoir I. So, you have the flood control requirement, you have the maximum release requirement, and you have the benefits associated with the release from a reservoir, the storage available in the reservoir, as well as the flood freeboard that you keep in the reservoir. Now, this is the typical problem which we will formulate as an optimization problem now. Associated with unit release, you have the benefits from each of the reservoirs. Associated with the flood freeboard that you maintain during the flood season, you have a benefit, associated with unit flood storage that you maintain, you have a benefit. Associated with the storage, because of the hydropower, you have benefit at each of the reservoirs. Now, these benefits need not be always economic benefits, they can be intangible benefits, they can be physical quantities and so on. But right now you just assume that they are returns that are provided, or something that something good that happens because of these particular variables like release, storage, flood control storage and so on. With these this understanding of the system, we will formulate an optimization problem which will decide the release policies or the reservoir operating policies at each of the reservoirs, reservoir 1, reservoir 2, reservoir 3, not separately, but together. That means, when I am saying this is optimal release at reservoir number 1, it has taken into account its implication or the operating policies implication on the downstream reservoirs and on all the other reservoirs in the system. So, that is how we formulate the problem as an optimization problem and solve it to obtain the reservoir releases at each of the reservoirs in the system. What I demonstrate through a simple 3 reservoir system can be generalized to any n number of reservoirs, because the principle remains the same. You look at the continuity, you look at the objective function and then formulate the optimization problem. So, we will continue this discussion, and in the next class I will start with formulating the optimization problem for this. So, essentially in today's class what we did is that we started with the LP formulation, linear programming formulation for obtaining the storage yield function. That is, we maximize R and then look at the storage yield function, which was done in the last class. I just explained it today, but we specifically discussed the reservoir operation problem at some length today in today's lecture. We started with the standard operating policy, where we recall that in standard operating policy for a reservoir, we do not look at other periods. We simply look at the current time period, look at the water available, storage plus the inflow, compare it with the demand and meet the demand to the best extent possible. That is the standard operating policy, without bothering about what is likely to happen in the other time periods within the year. Then we formulated a linear programming problem for the same issue of obtaining the reservoir operating policy, where we look at maximization of RT, sum of RT releases for the time periods within the year, subject to all the standard constraints, and obtained the storages that need to be maintained at each of the time periods and the associated releases during each of the time periods. This will specify the operating policy for the reservoir, and we provide typically what is called as a rule curve for the reservoir operators. The rule curves will indicate in general the reservoir storage to be maintained at the end of each of the time periods. For example, at the end of June, at the end of July and so on. And then towards the end of the lecture, I just introduced a multi-reservoir system, where we are looking at integrated operation of multi-reservoir systems. You may have multiple purposes at each of the reservoirs, and each of the reservoirs has its own objectives of operation, and you look at this particular system as an integrated whole, formulate an optimization problem and obtain the reservoir operating policies for each of the individual reservoirs. In the next lecture, we will start with this problem and formulate now an optimization problem, and typically a linear programming problem, and solve it to get the reservoir release policies at each of the reservoirs. Thank you for your attention.